Hello friends, welcome to AS Tutorials. Today we are going to solve some problems on root locus method. Sketch the root locus for the system having g of s into h of s is equal to k into s to the power 2 plus 4s plus 20 divided by s into s plus 1, and also determine the value of k so that the dominant pair of complex poles of the system has a damping ratio of 0.5. Corresponding to this value of k, determine the closed loop transfer function. In this problem, first we need to sketch the root locus, and from the root locus we need to find the value of k for an damping ratio of 0.5, and then for this value of k we need to determine the closed loop transfer function. First we are going to sketch the root locus. Given open loop transfer function g of s into h of s is equal to k into s to the power 2 plus 4s plus 20 divided by s into s plus 1. To sketch the root locus, we know that first we need to identify the number of poles and number of zeros. In open loop transfer function, the numerator s terms are considered as zeros and the denominator s terms are considered as poles. In this problem, in the numerator, a quadratic equation is given. From this, I am going to get the two complex zeros, and in the denominator, two s values are given, that is two poles are given. And in this problem, we are going to find the angle of arrival because complex zeros are given. In the previous problem, we calculated the angle of departure when complex poles are given. So remember, whenever we are having complex poles, then we need to calculate the angle of departure, and when we have the complex zeros, then we need to calculate the angle of arrival. In this problem, we are going to calculate the angle of arrival. So you can see here the number of poles are 2, number of poles are 2, that is s is equal to 0, s plus 1 is equal to 0. This can be written as s is equal to 0, s is equal to minus 1. Number of zeros are 2, that is s square plus 4s plus 20 is equal to 0. From this quadratic equation, I am going to get two complex zeros, that is s is equal to minus 2 plus j4, and the second complex pole s is equal to minus 2 minus j4. These are the two complex zeros I am getting from this quadratic equation. Now in this we can see the number of poles is equivalent to number of zeros, therefore capital N, therefore the number of branches capital N is equivalent to 2. Next we are going to plot the pole 0 plot, and then we are going to identify the root locus path. Next we are going to plot the pole 0 plot, and then we are going to identify the root locus path. On this I am going to locate the poles and zeros location. As we know, poles location s is equal to 0, that is at the origin s is equal to 0, and the second pole s is equal to minus 1, s is equal to minus 1, and 0 complex 0 s is equal to minus 2 plus j4, s is equal to minus 2 plus j4, and the next 0 location s is equal to minus 2 minus j4, minus 2 minus j4. So here I have shown the complex zeros, that is at minus 2 plus j4 and minus 2 minus j4. So we have located the poles and zeros location. Next we are going to identify the root locus and no root locus path. From this point to this point, I am not having any poles or zeros, that is the count is 0. 0 is an even count. For this point to this point, I am going to consider no root locus path. And at this point I am getting one pole, that is count is 1. 1 is an odd count. From this count to next count, I am going to consider the root locus path. Now at this point the count becomes 2, that is even count. From this count to next count, I am going to consider no root locus, but here we can see here on the real axis I am not having any pole or 0 till infinity. Therefore from this point to till infinity I am going to consider no root locus path. So in this way we have identified the root locus path and no root locus path. Next we are going to see the number of branches approaching to infinity. As we know, number of poles minus number of zeros is equivalent to branches approaching to infinity. In this case, number of poles are 2 and number of zeros also 2. Therefore, 0 branches are approaching to infinity. 0 branches are approaching to infinity. So when there is no branch approaching to infinity, then we are not going to calculate angle of asymptotes and centroid. We know that we are calculating the angle of asymptotes only when any branch is approaching to infinity. If we are calculating the angle of asymptotes, then we are calculating the centroid to draw that angle of asymptote. In this, I am not having any branch which is approaching to infinity. Therefore, I no need to calculate angle of asymptote and centroid in this problem. In this problem, the starting point is 0 and minus 1 and ending point, the 0 location is minus 2 plus j4 and minus 2 minus j4. So the poles originate at 0 and minus 1 and ends one with minus 2 plus j4, and the other pole ends with minus 2 minus j4. Next I am going to calculate the breakaway point. As we know, in this problem we are having more than one branch, therefore I may get the breakaway point. Next I am going to calculate the breakaway point. As we know the procedure to calculate the breakaway point, that is, we need to consider the characteristic equation 1 plus g of s into h of s is equal to 0. In this problem, we know g of s into h of s is k into s to the power 2 plus 4s plus 20 divided by s into s plus 1 is equal to 0. So by taking LCM, we will get s. Now this denominator term goes to right hand side, becomes 0. Now here I will be getting, now here this s square plus s I am going to take to the right hand side, k into s square plus 4s plus 20 is equal to minus s square minus s. This term I will take to the denominator, then k is equal to minus s square minus s whole divided by s square plus 4s plus 20. Now I need to differentiate this k equation. It is in u by v form. Differentiating this k equation with respect to s, dk by ds is equivalent to, I am going to keep this denominator constant, s square plus 4s plus 20, and differentiating numerator, minus s square is minus 2s minus s is minus 1 minus, keeping numerator constant, minus s square minus s, differentiating denominator, I will be getting s square differentiation is 2s plus differentiation of 4s is 4 whole divided by s square plus 4s plus 20 whole square is equal to 0. This denominator term goes to right hand side, becomes 0. So by multiplying this numerator equation, I got this equation. In this, minus 2s to the power 3 plus 2s to the power 3 get cancelled, and in this I am having minus 8 square minus 8s square minus s square, that is minus 9s square plus 4s square plus 2s square. I am going to get here minus 3s square, then minus 40s minus 4s minus 44s, then plus 4s, I am getting here minus 40s, then minus 20. So and then you can see here I am having only one constant value, that is minus 20 is equal to 0. This is the dk by ds differentiation of k equation with respect to s I got. Now for this I am going to find the root values. Here I got the differentiated value 3 minus 3 s to the power 2 minus 40s minus 20 is equal to 0. By taking minus common 3s to the power 2 plus 40s plus 20 is equal to 0. For this the two root values I am going to get s is equal to minus 0.52 and the second root value s is equal to minus 12.81. I need to check this breakaway points whether they are valid or invalid by substituting in k equation. As we know, if we are getting the complex breakaway points, then we need to check the validity by angle condition, but in this I am getting both real values, therefore I am going to check the breakaway points are valid or invalid by substituting in k equation. So here I will be considering k is equivalent to s square minus s divided by s square plus 4s plus 20. First I am going to consider the first value, s is equal to minus 0.52. For this I am getting k is equivalent to 0.01, that is positive value I am getting. Therefore s is equal to minus 0.52 is a valid breakaway point. Next I am going to check for the second value, k is equal to minus s square minus s divided by s square plus 4s plus 20. Here I am going to substitute the second value, that is s is equal to minus 12.81. For this I am getting k value minus 1.138. You can see here I am getting negative value, therefore s is equal to minus 12.81 is a invalid breakaway point. So I got one breakaway point, valid breakaway point, that is s is equal to minus 0.52. Next I am going to calculate the intersection with imaginary axis. To calculate the intersection with imaginary axis, we need to apply the Routh method. For Routh method, first we need to consider the characteristic equation, that is 1 plus g of s into h of s is equal to 0. 1 plus g of s into h of s is k into s to the power 2 plus 4s plus 20 divided by s into s plus 1 is equal to 0. Now by taking LCM, s into s plus 1 plus k into s square plus 4s plus 20 whole divided by s into s plus 1 is equal to 0. By taking this denominator term to the right hand side, it becomes 0. Now by multiplying this above equation, I will get, from this I am going to get, so 1 plus k into s square in these two terms, and in these two s terms by taking s common I will be getting plus 1 plus 4k into s plus 20k is equal to 0. This is the characteristic equation I got. Now I am going to form the Routh's array. Now we know to form the Routh array we are going to consider the highest power from this characteristic equation. In this the highest power is s to the power 2, that I have considered here s to the power 2, and the other powers I have considered in decrementing order, that is s to the power 1 and s to the power 0. Now I am going to form the two rows directly from this characteristic equation. For that we know here a0 coefficient is equivalent to 1 plus k and a1 coefficient 1 plus 4k and a2 coefficient 20k. So in the first row we are going to consider the even coefficient, that is a0 and a2. a0 value is 1 plus k and a2 value is 20k, and then in the second row we are going to consider the odd coefficient, that is a1. a1 coefficient is 1 plus 4k and I am not having a3, therefore here we will consider 0. Now the last row we are going to get by multiplying this term with this and this term with this, and we know when we get 0 in the diagonal, then the resultant value is the above value, that is directly I can write in s to the power 0 row 20k. Now we know from this, from s to the power 0 20k greater than 0, that is k greater than 0. Then from s to the power 1, here we are having 1 plus 4k is equal to 0, that is here I am getting 1 is equal to minus 4k, here k is equivalent to minus 1 by 4. So here I am getting negative k value, therefore I am not going to get the intersection with imaginary axis. So in this I got k is equal to minus 1 by 4, that is k margin is equivalent to minus 1 by 4. K margin is negative. Root locus branches are not intersecting the imaginary axis but always located in the left half of S plane. Therefore the stability range is 0 less than k less than infinity. Next we are going to calculate the angle of arrival. Angle of arrival: the angle at which the branch or locus arrives at the complex 0 is called angle of arrival. It is denoted by phi a. The procedure to calculate the angle of arrival, as it is same what we did for angle of departure. In this you can see in place of complex poles I have considered complex 0, that is minus 2 plus j4 and minus 2 minus j4, and I have located the pole location, that is s is equal to 0 and s is equal to minus 1. Now I am going to calculate the angle of arrival either at this point or this point. As we know, the value what I am going to calculate at this point will be same at this point with opposite sign. If I am calculating angle of arrival at this point and then the value what I am going to get at this point, it will be same at this point with opposite sign. Any one point I am going to consider. Now in this problem I am going to consider at this point I am going to calculate the angle of arrival. So the formula for angle of arrival is 5a is equivalent to 180 plus 5. In angle of departure the formula was angle of departure is equivalent to 180 minus 5. In this angle of arrival the formula is 5a is equivalent to 180 plus 5. Now the procedure is same. We are going to consider this point and I am going to join all the roots towards to this point. That is, by joining this 0 to this point I am going to get the first angle, that is phi z1, and then I am going to join this pole towards to this point, then I am going to get the first pole angle, that is phi p1, and from this pole to this point I am going to join, from this I am going to get the second pole angle, that is phi p2. So I am going to join this all these roots towards to this point. So by joining this 0 towards to this point I am going to get first 0, that is phi z1, and then I am going to join this pole towards to this point. From this I am going to get first pole angle, that is phi p1, and I am going to join this pole, second pole towards to this point. Then from this I am going to get the second pole angle, that is phi p2. Here I got first 0 angle phi z1, at this point I got first pole angle phi p1, at this point I am going to get second pole angle, that is phi p2. Now we know the formula for angle of arrival. Phi a is equivalent to 180 plus phi. The phi formula is phi is equivalent to summation of phi p minus summation of phi z. In this problem summation of phi p is equivalent to phi p1 plus phi p2, phi p1 plus phi p2, and the phi p1 value is phi p1 is equivalent to, in this case both the angles are unknown, therefore phi p1 is equivalent to 180 minus tan inverse. In this you can see that at this point the opposite tan inverse opposite by adjacent, so opposite is 4 and adjacent value is 1, so tan inverse 4 by 1, this will be equivalent to phi p1 is equivalent to 180 minus tan inverse 4 by 1, that is tan inverse 4 value is 75.96. Therefore here 5p1 is equivalent to 180 minus 75.96 is 104.04. Next I am going to calculate 5p2. This is the 5p1 value. Next I am going to calculate 5p2. 5p2 is equivalent to, in this also you can see two angles are unknown. Therefore 180 minus tan inverse, opposite is 4, adjacent is 2, 4 by 2. This will be equivalent to 5p2 is equivalent to 180 minus tan inverse of 2 is, we are getting 63.43. Therefore 5p2 is equivalent to 180 minus 63.43 is 116.57. So I got the second pole angle, that is 5p2 is equivalent to 116.57. Next I am going to substitute. Now I am going to substitute this 5p1 and 5p2 in this above formula, that is summation 5p is equivalent to, 5p1 value is 104.04 plus 5p2 value is 116.57. Therefore summation of 5p is equivalent to 220.61. Now this is the summation of 5p I got. Next I am going to calculate the summation of 5z. In this I am having only one zero angle, that is 5z1 is equivalent to, directly I can write 90 degree. Therefore summation of 5z is equivalent to 90 degree. Now by substituting this summation of 5p and summation of 5z in this formula, I will get summation of 5p is 220.61 minus 90 degree. This I am getting here, 5 is equivalent to 220.61 minus 90 degree. I am getting here 130.61. Now by substituting this 5 value in this angle of arrival formula, that is angle of arrival is equivalent to 180 plus 5. Now I got the 5 value, angle of arrival 180 plus 130.61. Therefore here angle of arrival is equivalent to, I am getting 310.16 degree. This angle I am getting at minus 2 plus j4. I got angle of arrival 310.16 at minus 2 plus j4, that is at this point. Now as I told that the same angle I am going to get at this point with opposite sign, that is angle of arrival is equivalent to minus 310.16 degree at minus 2 minus j4, minus 2 minus j4. This is the angle of arrival I got, that is 310.16, and at the other point I got the minus 310.16. Now at this angle the branches are going to arrive to this 0 location. Next we are going to sketch the root locus. Now in this we have calculated, as we know that starting point 0 minus 1 and the ending point for this 0 and minus 1 is minus 2 plus j4 and minus 2 minus j4, and we calculated the valid breakaway point, that is s is equal to minus 0.52. Then we calculated angle of arrival. These are the calculations we have done to sketch the root locus. Here I have considered the scale, x-axis is x-axis. Here I have considered the scale, x-axis 1 unit is equal to 0.5 centimeter and y-axis 1 unit is equal to 0.5 centimeter. Now first I have located the pole location, that is s is equal to 0 at the origin, and then the second pole at minus 1, and then 0, that is at minus 2 plus j4, minus 2 plus j4, and the second complex 0 minus 2 minus j4. Now as we know that when the input is applied, this pole moves in this direction and this pole moves in this direction, and they are going to meet at one common point that we called breakaway point, that is S is equal to minus 0.52. At this point the branches comes out, one comes out above and the other branch comes out below. See here, this branch is arriving towards to this 0 by following an angle 310 plus, by following an angle 310.61 degree, whereas here you can see that this branch is arriving to this 0 by following an angle minus 310.61. In this way branches have approached to 0 location. Now next we are going to calculate the K value from this graph for a damping ratio of 0.5. For that we need to consider here cos theta is equivalent to zeta. Cos theta is equivalent to zeta. Here the zeta value we know that in the problem is given 0.5. So theta, angle theta is equivalent to cos inverse of 0.5. Cos inverse of 0.5 is 60. Therefore theta is equivalent to 60 degree. We are going to draw 60 degree angle from this origin from the left hand side. $60 we are going to mark here, and so this is the 60 degree angle we have drawn. Now here the angle which is intersecting the locus, from this point we are going to get the imaginary value, and at the same point we are going to get the real value. Here the point which is intersecting, the angle which is intersecting with locus, we are going to consider it as a point P, and the value, imaginary value, you can see here 1 unit 0.5 means the imaginary value I am getting 1, and the real value I am getting here minus 0.5. So minus 0.5 plus, here the value is J. So this I'll be considering 1J. This point I am naming as a point P. So the value I got here minus 0.5 plus J. So in this way we are going to find the dominant poles. Now for this pole I am going to find the K value. The same, if I draw the 60 degree angle in the below axis, then I am going to get the point minus 0.5 minus J. So now we have calculated the dominant poles. Remember, in this problem the angle is intersecting only at one point. If the angle is intersecting with the locus twice, then we need to consider that point also. In this you can see that nowhere this angle is intersecting to the locus, only once it is intersecting. Therefore I have considered that as a point P. If there is a 2 intersection, then I need to consider that point as a Q, and I need to note down that value, and for both I need to find the K value, K1 and K2. Now in this problem only the angle is intersected with the locus once, therefore I am naming that point as a P, and the value is minus 0.5 plus J. Now for this value I am going to calculate the K value. Now by applying a magnitude condition, I am going to find the K value for this point. Magnitude condition, that is the magnitude of G of S into H of S is equal to 1. Magnitude of G of S into H of S, in this case K into S to the power 2 plus 4S plus 20 divided by S into S plus 1 is equal to 1. Here as we know that for this numerator quadratic equation we got the two complex values that I am going to write here. K into S plus 2 plus J4 into S plus 2 minus J4 whole divided by S into S plus 1. Now here I am going to substitute the S value. The intersection value what I got, that is S is equal to minus 0.5 plus J. Now by substituting S value in this, I will be getting magnitude of K, magnitude of S value is minus 0.5 plus J plus 2 plus J4. Next second value, magnitude of S value is minus 0.5 plus J plus 2 minus J4 whole divided by, here in this S, magnitude of S is minus 0.5 plus J, then this S value minus 0.5 plus J plus 1 is equivalent to 1. Now here in this I am going to get here this magnitude of K as it is minus 0.5 plus 2, I am going to get 1.5 plus J plus J4, I am going to get plus J5, and then in this minus 0.5 plus 2, 1.5 plus J minus J4, I am getting here minus 3J, J3 divided by this as it is minus 0.5 plus J, and here I am getting minus 0.5 plus 1, that is 0.5 plus J is equivalent to 1. So magnitude of K is K, and magnitude of 1.5 plus J5 is, I am getting 5.22 into next 1.5 minus J3, magnitude of 1.5 minus J3 is 3.354 divided by magnitude of minus 0.5 plus J value is 1.118, and then the magnitude of 0.5 plus J value is 1.118 is equivalent to 1. So by multiplying this, I am getting here in the numerator K into 17.50 divided by 1.18 into 1.118, 1.118 into 1.118, I am getting 1.249 is equivalent to 1. Here further I am getting K value, K is equivalent to 1.249 divided by 17.50, this will be equivalent to 0.07. This is the K value I got for damping ratio is equivalent to 0.5. Next, for this K value in the question it is asked to find the, next in the question it is asked to, for this K value in the question it is asked to calculate the closed loop transfer function. So next I am going to find the closed loop transfer function by considering this K value. So in this dominant pair of complex poles from the graph I got, that is at the intersection of locus and the angle of theta, I got S is equal to minus 0.5 plus J, and the other pole value I got S is equal to minus 0.5 minus J. These are the two dominant pair of complex poles. This can be written as S plus 0.5 minus J, and then this can be written as S plus 0.5 plus J. So these are the two poles I got, dominant poles. Now for this I need to find the closed loop transfer function by considering the K value. Here I got the K value, K is equivalent to 0.07. So the transfer function for the damping ratio of 0.05, I am getting transfer function is equivalent to K divided by, I got here these two dominant poles, S plus 0.5 minus J into S plus 0.5 plus J Now k value we know, k value is 0.07 whole divided by multiplying these two dominant poles, I am going to get s square plus s plus 1.25. Now this is the transfer function for the value of k is equal to 0.05 for a damping ratio of 0.5. In the problem, if it is asked to find the natural frequency, then we are going to compare the denominator characteristic equation with the standard characteristic equation, that is s square plus 2 zeta omega ns plus omega n square, and in this the characteristic equation I got s square plus s plus 1.25. By comparing with this standard characteristic equation, omega n square is equivalent to 1.25, that is omega n is equivalent to root of 1.25. so omega n is equivalent to root of 1.25 is 1.11 radians per second. So if in the problem it is asked to calculate the natural frequency, then in this way we are finding the natural frequency. Hope you understood this problem. For more such videos, like and subscribe my channel. Thank you.